Time for a pop quiz. Huh, nicely integrated. Hardly even a practice test. Problem solved. Easy as pie.
Hello everybody, my name is Penn Center. We're back for a little bonus mathematics stream requested by the one and only E to the 2i pi. Hopefully you're all doing well and enjoyed our introduction class to real analysis this morning, co-presented by yours truly and McKenna from the Mandelbrot Mathematics server. Again, big shout-outs to everyone that popped by this morning. Zone, appreciate the resub. Thank you for the most recent followers as well. Emac, Vidig, and we had a big raid pop in today too from Javaqua. Shoutouts to everyone. We are just about to head in and do some mathematics. Someone is thrilling in math today. Yeah, there's so much math happening today. It's crazy. What a crazy Saturday this is. I don't have any specific plans for today's stream. Let me erase something so it's off of my working memory. Boop. You have a question for me. Shoot. Please tell me your question. I did field a question today that I was not able to answer. Very confused by a question on Math Olympiad. Okay. If you are able to post it into one of our shared servers somewhere and let me know where it is, we can take a peek. Did I spell that wrong? Oh, I just wanted a capital letter. Where is the question? Where is the question? Prove the T is linear and find bases for both the null, I think this is rank and null space of the transformation, then compute the nullity and rank. So that's the dimensions. That must be the row space and the, wait. I have to look up what this notation is. So while you find that question, Lucas, I will take a look at what this notation is. So let's see. Downloads, where are my textbooks at? Where's my linear algebra? I think this is like 2.1. Null space and range. It's the range. Okay, so it'd be null space and range, I believe, is what they want us to look for. Okay, that's linear.
Problem solved.
There it is. Okay, so it'll be the... Let VNW be if ND and RT are finite dimensional. Okay, so where's the definition of... Yeah, null space or kernel, and then the range and image. Okay, got it. Fem, welcome back. Been thinking about it for 5 hours? Oh, damn. Well, hopefully you find it. It was low-hanging fruit, so you did it. That's fine. Totally fine with me. We should do one of these. Let's do one that's like not a vector space. Let's do like either 4 or 5, I think. Once you get it posted, Lucas, let me know, and we'll go hunt it down. A matrix space or a polynomial space? Maybe a polynomial space. That seems like fun. This is x times f of x plus f prime. That seems potentially fun. I mean, it could also be potentially challenging. So first things first, we're going to prove that it's a linear transformation. So we have a transformation from polynomials of degree no more than 2 to polynomials of no more than degree 3 with coefficients over the real numbers. So let's take a function. We're going to call it, well, I don't really want to use f of x, but let's take a polynomial inside of P2R. Actually, don't we need a couple? Let's take a couple. Let's call them P and Q. And let's see what happens to T of CP plus Q. Now T should naturally send this to x times the input plus the derivative of the input. So this is going to get sent to x times the input plus the derivative of the input. Okay, I'm just going to use prime notation. So I guess that means for the first part here, we're going to get like cxpx plus xqx. And then the derivative is going to distribute linearly, so we're going to get cp prime of x plus q prime of x. So let's rearrange that. So let's factor out a c. If I factor out a c from a couple terms, we're going to get x p of x plus p prime of x. And then the remaining terms should be xq q plus q prime. And then we can see that this really is ct of polynomial p plus t of polynomial q. So it is linear. That's kind of cool. Found it. Nice. Okay. Good timing. Okay, so we know that t is linear. Then what do they want us to do? Find bases for both the null space or kernel and the range. No, it's not a problem. Then compute the dimensions and verify the dimension theorem. Finally, use the appropriate theorems in this section to determine whether t is 1-to-1 or onto. Okay, this is a big question. So we need to find the kernel next, and then the range. These should be pretty much perpendicular spaces, or at least they shouldn't contain each other, so they're going to be mutually exclusive. So to find the null space, or the kernel, we'd have to figure out all the polynomials that get sent to 0. So we need to find t of p is equal to the 0 polynomial. You can post them in the same forum post if you want to, Lucas, if that's easiest. So we know t sends a polynomial to x times that polynomial plus its derivative. We want that to be equal to 0. Ooh. I suppose we're probably going to have to use the fact that p now has the highest order of 2. Hey, I mean that's a fun thing to do. Some of these questions are really hard though. Okay, so we've picked a specific polynomial of at most degree 2, found its derivative, and made a substitution. So what are we going to get here? We are going to get an ax cubed plus bx squared plus cx plus 2ax plus b is 0. So can we collect? We can collect some like terms here. So bx squared plus, let's go 2a plus cx plus b. So we can see right away that a has to be equal to 0 and that b has to be equal to 0 for this to work. And I guess if a is equal to 0, that is going to force c is equal to 0 as well. That's crazy. So that really just means that the kernel, or the null space, is literally just the 0 vector, the 0 polynomial. Cool. All right, where are you posting stuff, Lucas? Wait, otherwise ln p prime equals negative x? Oh gosh, what's happening? What? No, don't do it. The derivative of ln p prime equals negative x. That sounds nasty. You're saying just enough that I'm curious about how you're thinking about something, but I'm also wondering if you're just trying to troll me. It's been a long morning. Okay, so I think that's the best we can do with the null space. So that means that the nullity would be 0. Posted it in the math forum on the elements. Okay, let's take a peek. Maths forum. Boop. Oh, that's a lot of questions. Okay. 4, 12, 15, 23, 25, 26. Damn. Okay, so n square a, b, c, d, m Does that say M is the midpoint of CD? Okay, so if M is the midpoint of CD, what is the length? No, what is the angle measurement of BAM? The tangent? Yeah, that's what I'm wondering too, Jasu. I wonder if it's like the tangent of the angle, right? Like tan of angle BAM. Okay. So we have a square. I assume it's a square. Virka? It looks like a square. Oh, sorry. And how do we label the square? So A, B, C, D that way. So A, B, C, and D. We're going to create a midpoint here called capital M. And we're curious about this angle here. I'm just going to call it maybe alpha. So we want to calculate tan alpha. That's our goal. So what do we know? We know that this and this should be the same size.
Look at me!
And if M is the midpoint, we could probably also construct...
Why did you even rope me into this? Because he roped me into this! Well, him over there, he roped me into this! Well, he roped me into this!
I know, Lucas is getting around, Rex. Lucas is bouncing from channel to channel, being like, who wants to do Olympiad questions with me? Yeah, so I would say let's just construct the line segment from B to M. I know that that also has to be alpha. So now we have an isosceles triangle. And then it doesn't particularly matter the side length of the square. These angles are not going to change. They're always going to be consistent. So we could call this length here length 1 if we wanted to. And since M is the midpoint, we know that this length, for example, is a half. Okay, here's a right-angled triangle. Now, it might be more beneficial for us to scale up our diagram by 2. Yeah, Poingala says take 2, exactly. So I'm looking at this fraction going, I don't really like that. So why don't we scale this up by 2 so that we get 1 and 2, and then maybe someone can tell me what that missing angle is, or missing side length is. Yeah, good thought, Poingala.
QED.
Very good thought. Is it 5?
Zeta. Sharp choice. 5 could be a number or an evaluation of your response. Either way, it's a solid figure in math. What's your angle here?
Yep, there you go. So I agree that we got 2 squared plus 1 squared, so we should get 5. Yeah, so 2 squared plus 1 squared is equal to a squared plus b squared equals c squared, right? Our hypotenuse squared, so this is 5. Okay, so we'll take positive root 5 for that side length. Okay, so that's going to give us a bit more information about these triangles. What's this distance? So if I was to make a 90-degree angle, like just kind of drop this as a 90-degree angle, what would this distance be here? I think we could take that as... 2, right? Wouldn't that make sense? Sweet, so that should give us all the info that we need to work inside this triangle where we know alpha exists. So this is going to be 1, right? It should be the same length as what we have up top. So we're really working with a triangle that looks kind of like this, right? Here's our alpha. We have 1, 2, root 5. And so we need tan of this angle. So tan of this angle is opposite over adjacent. So it should be 2. I'm going to try to avoid tans. You don't like to get out in the sun that much. Also, enjoy a QED point
Easy
as
as
a thank you for
pie.
posting some questions, Lucas. Oops, that's not what I want. All right, so if we're asking for the tangent of angle BAM, I believe the answer should be 2. Sweet. Maybe I can give myself a QED point. Okay, let's try one more here. And we'll try to finish off that linear algebra question. Okay, number 12. So something about adding some stuff up. So we have some hidden numbers, A, B, and C. We're going to add those numbers up. And we need to know the product of A, B, and C. That's kind of cool. You QED'd first? There you go.
Hardly even a practice test.
Have another QED. Okay, so we need A, B, B, C, C, and all that added up. This is 12. A, B, B, and C, C, all of that added up is A, B, C? A, B, C? And our goal is A times B times C. That's what I'm wondering, Jesu. Do we have any other information that we can get here, Lucas? So it just says something like A, B, C. Right, like it looks like it says like they add to some number. Are there any stipulations on A, B, and C? Like they have to be a digit, or they have to be like 0 through 9?
Zeta clever. If A, B, and C aren't 0, then you're onto something significant like a
Okay.
quadratic equation. What's your calculation or conundrum with these variables?
Yeah, okay, so A, B, C not 0 would definitely make sense because we know this product is going to be not 0. Okay, so A, B, and C are not 0. Does it say that A, B, and C have to be different numbers? Have to see the question, sure. So I'm wondering, do A, B, and C have to be different numbers, or could they be the same? Could they be the same? They could be the same, okay. So let's take a look at this first. This is interesting information. So we know that A plus B plus C is equal to C as digits. And these are digits between 1 and 9. So what does that tell us about A plus B? A plus B has to be equal to what? Jag, you're close. I think A plus B has to be 10. I think it's got to be 10. Because if A plus B was equal to 10, right, when I added those numbers together, then I'd capture the C back again. Right, so basically I'm kind of thinking like this. I know my final answer is going to be A, B, C. And so A plus B plus C is like C, but I have to carry the 1 over, right? So I'm getting like C-teen, C-teen, you know? It's like it's 11 or 12 or 13 or 14 or something like that. And so next I think we want to kind of look at what's happening here and see if we can make some argument as well. So we know that A plus B plus C plus the carryover 1 is equal to 10 A's plus B. Oh, Rex, you bring up a very good point. Is it possible that A plus B could be 20? Or is it possible for us to have A, B, C arranged in such a way? So what's the biggest that A, B, and C can get? So the biggest C could be is 9, right? And then these other two numbers have to add up to something that's going to give a carry.
In arithmetic, a carryover is necessary when summing digits exceeds their base value. Now keep it simple, or it'll become zeta chaotic.
I think the problem is we're never ever going to be able to get a 20. Right, because if I match up these digits and then I force another number in here, that gives me 17 right now. But the only way that I can match up this digit is to put a 2 here, right? I can't put more, right, if my digits are forced to be between 1 to 9. So I think I'm stuck. I don't think we're going to get a 20. I think a 10 is the best we can get. Yeah, single digit. Yeah. And Jasu, I agree with you. We need the carryover to be A. Exactly. So I'm trying to model that here, right? So the carryover is going to be whatever digit I get for A, but I'm going to multiply that by 10. So I'm going to move it over a place value. So that's what this 10A means. We're going to move A over by 1 place value. So if we subtract B from both sides, this tells me that A plus C plus 1 is equal to 10A, or that C plus 1 is equal to 9A's. Oh, I see. Maybe it's better if we try to do A, B, C, 1, and B. Because this is the carryover thing. What if we did the A, B, C, and 1? So what if I forced A plus B plus C plus 1 to equal B? Then I'd have A plus C plus 1 is equal to 0. A plus C is equal to -1. That's not right. Oh, this isn't 0. This is 10. So A plus C should be 9. So is that enough to get what we want? So does this system of 3 equations give us something reasonable? So this would give a equals 9 minus c, and if we sub that in, we get c plus 1 is equal to 9. 9 minus c, so c plus 1 is equal to 81. Minus 9c, so 10. C is equal to 80, c is equal to 8. Potentially. I'm just going through some of the algebra now. So if c is equal to 8 and a plus c is equal to 9, then a is equal to 1. And if a is equal to 1 and we know that a and b sum to 10, then b must be equal to 9 as well. B must be equal to 9, sorry. So I'm thinking maybe a is 1, b is 9, and c is 8. So let's see if that works. If I do 11 plus 99 plus 88, what do we get? We get 18, 10, 18, 19. Did it work? I think it's okay. I don't know why. Okay, I don't know why Automod is going crazy today, but every time somebody types square into chat, Automod's going crazy.
A2 plus AC plus C2. Now that's a Zeta elegant expression. Any currents swirling in your math mind?
Could we say that 2a plus 2b equals... So 2a's plus 2b's plus 2c's... Yeah, so Lucas, we could do something like that. It would look like this. It would be a little bit different, I think, from what you have written down. You could say that a plus b plus c, so that's the single digit, and then we could add the tens to it, so 10a's plus 10b's plus 10c's. That's going to be the second column. All of that would have to equal 100a plus 10b plus c. So you could theoretically use that equation. So that would be permissible. By the way, 1 times 8 times 9 is 72, right? So we're looking, I think, to see if there's an answer of 72. So I'm thinking the answer is D, by the way. Banned you for using the word expensive? Jeez. That's crazy, man. That's nuts. Yeah, I don't know. Like, literally, like, 4 people have come into chat and talked about, like, square or, like, a squared or something like that, and, like, Automod keeps stopping the conversation for some reason. I don't know why. But yeah, so Lucas, I think the point here is you try to create as many equations as you can. We need at least 3 that will solve the system. So I did the units digits added together to get a plus b is 10. I did the tens digits added together here to get a plus c is 9. And then I redid the tens digits to do 10a plus b. So that gave me my third equation. But what you suggested over here would work as a third equation as well. We just need a third equation in order to finish the job. Maybe what I'll do for you along the way is I'll kind of post some of the solutions that we've done so no one... Okay, so number 4. Number 12. Okay, we'll come back and we'll take a look at 15 in a second. Is that on the same sheet? Yes. Okay, I want to finish up that linear algebra question. I feel like we're pretty close. So our linear algebra question was polynomial defined in this particular way. We found the null space. The null space is just the 0 vector. So that means that the row space should be all of t, right? Like all of P3. And there you go. So rank nullity, our dimension theorem, right, should line up, and I do believe that should work. P3 means the highest degree is 3 in that polynomial. Yes, that's correct. I just wanted to finish. I wanted to get that out of my brain, so that I could help Lucas with some stuff. So if you're curious, I'm just in the simple server right now. I'm just kind of answering some stuff from the Friedberg, in the problems forum of the Friedberg reading group. So I'm just kind of scrolling down to the older posts and just kind of starting to answer some of these older questions from chapter 2, just in case people want to see a couple answers. So the next linear algebra style question I want to work on is this one. Prove that there exists a linear transformation from R2 to R3 such that T of 1, 1 is this, and T of 2, 3 is this, and then we want to find T of 8, 11. I mean, we could prove the existence by just finding it. Poingallis, what are we asking? So it can't be 3. Are you discussing the P3 question? So the dimension of P3 is 4, right? Right, like it's going to be an ax cubed plus bx squared plus cx plus d. So it's going to have four parameters that we have to worry about. And I guess if the kernel's nothing, right? If the kernel is only the 0 vector, then we know that the transformation should have. Oh, right. I understand what you're saying now. How can the rank be 4? The rank can be 4 because we're putting it. The rank could be 4, couldn't it? I only have 3 basis vectors. 3 basis vectors. I can't magically produce a basis vector. Did I mess up something in my... Did I mess up something in my nullity question? I think I understand what you're saying now. So if I take a polynomial of at most degree 2... Okay, so it's not the nullity that's the problem. And it should be... I see. So the dimension of the range is going to be the dimension of P2 by the dimension theorem. So I need to figure out a basis for the range. That's what I skipped. Okay, yeah, I understand. I got you now. I got you. It definitely can't be dimension 4 because I don't have 4 basis vectors in P2. That's correct. So the range is not all of P3, so I cannot say that. Can I say anything about the kernel being... I do know the...
Well, that one over there wrote me into this. Well, he wrote me into this.
I do know that the rank is going to be 3, right? And I do know that the nullity plus the rank... And I had the wrong dimension, right? It should be the dimension of the starting space. So it should be the dimension of P2. So 0 plus 3 should be equal to 3. So the dimension theorem should hold, but let's try to find a basis for RT. So if I toss a polynomial through this transformation, this is what happens. And this particular polynomial, we know we can write it as, say, ax squared plus bx plus c. And its derivative would be 2ax plus b. So what are we getting over on this side? We're getting like an ax cubed plus bx squared plus cx. We're going to pick up another 2a. So we'll get 2a plus cx's. And then plus a b. So this is what the range is going to look like. It's all the polynomials that have this form. Actually, that's not a bad idea too, right? We can actually maybe verify that that's true. Yeah, our basis vectors should theoretically go to basis vectors.
Test.
Since it's 1-to-1,
Zeta
right? That would be a little bit
impressive,
faster.
But don't get complacent. Try this. Solve 3-2, 12 and R0. What's the
3-2?
value of x? Show me your mathematical prowess or be lost in Zeta failure.
And so I guess we can kind of see that there are going to be probably 3 basis vectors here. We can kind of break this down
Zeta
into like
simple.
an A.
3k, 2 equals 5. Basic addition in a Zeta chaotic world. What's your next inquiry in this mathematical play?
So those are our 3 basis
Zeta
vectors.
unwise. Failure's just a step in the equation of success. Learn from it. Don't let it define you. What's your next inquiry into the realm of logic or numbers? Oh yeah? Prepare to be iterated.
Yep, so there it is. There's our 3 basis vectors. Now, out of curiosity, do we get these basis vectors just by pushing the standard basis through? So this is just me being curious, and it's probably true.
Straightforward. Solve for nice
Duff Dude, thank you very much for the follow.
First equation. On la seki, y star 7 extraction dirt work. Substitute into the second in there. Get 7. Eng dot 2, a jubilee d2 plus e
A jubilee d2.
11. Great.
A doobly dee
Simplify and solve.
Yeah, so these are indeed the basis vectors that we would get if we just pushed the standard basis through. Just out of curiosity. Yeah, I thought that might be the case, but I just wanted to double check. Okay, yeah, so Poingallus, that will work as well. Our basis vectors should get mapped to basis vectors because we know the kernel is just contains the 0 vector, right? So this should be invertible in the sense that it's 1-to-1, but it's not onto, right? Interesting. Now I'm kind of curious about what kind of polynomial we wouldn't be able to get picked up with this. So there'd be a specific form of polynomial we wouldn't be able to get, right? So what is it? Like as soon as we pick b... Oh, I see. It's because we don't have independence of the constant term and the x squared term, right? So the x squared term and the constant term are stuck together. Yeah. Is Showbot ill when he's pronouncing formulas? Yeah. I need to make show, because I think what happens is it goes over to, like, the interface goes to ChatGPT. ChatGPT is trying to text something up, right? Like it's using, like, LaTeX. And then when it ports it back into, like, actually being able to pronounce it, it just can't say anything because it's trying to tech everything. Okay, I feel much better about that question now. Thank you, Poingalis, for that. 15, Lucas was saying, is the one that's been tricking you all day. It's been tripping you up. Okay, you're going to really have to help me with how to think about this one. There's definitely a football. 12 regular-sized hexagons. No, 12 regular-sized pentagons and 20 regular-sized hexagons. Yeah, Euler's formula. That sounds about right. It's invertible because it's 1-to-1. Is basically what I was trying to get at. Injective doesn't mean it's in... Here. There. No, I wasn't clear. I know that the transformation is going to be invertible because I know it's 1-to-1. That's all. Yeah, I'm trying to figure out. It looks like Lucas popped away, and I know it's probably pretty late for Lucas right now too. But I want to get a quick translation of this. If you're there, Lucas, we could at him maybe. Otherwise, we're gonna pop over and do a couple more linear transformation questions. I mean, we should. You always thought that 1-to-1 is injective and surjective at the same time. Oh, we call that bijective for some reason. Too many things. Injective, I think, is 1-to-1. Surjective, I think, is onto. And then when you have both, it's bijective. So, like, I think RT is going to be, like, invertible in the sense that I can push something forward. I should be able to invert those things back, but it might not be able to invert everything backwards, right? So, it'll be invertible in the subspace, right, that it pushes these basis vectors into, the span of those basis vectors. That should be fine. Going to go to sleep? Okay. Can I get a quick translation of 15 so I can think about it? Quick translation of 15, hurry. Before you beds. Okay, I've just been translating it wrong all the time. Whoops. But I mean, like, isn't injective the only one that you really need for it to be invertible? I know, like, look at these crazy words. Sein, Zeeds, Z's. I don't even know how to say these. These crazy words. 12 5-squared thingies and 26 squared thingies, yes. And then I want to know the question. So it's like, how many something somethings? Something twee. So this is our 6-sided things, right? You can invert the subspace, right? You can invert the subspace that things get mapped into. How many sides are from two 6-sided thingies? Oh, I see. Oh, okay, that's cool. So it should be 1, 2, 3, 4, 5. So it should be 10. No, I should do it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it should be 20 plus whatever it is along that connector piece. So it's going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be like 30, I'm pretty sure. I'm pretty sure it's B. Yeah, that's what I'm trying to get at. Plangalis wrote it down. Right? If x from x to f of x is injective, right? It should be invertible, right? You should be able to find the pre-image of that. I guess all I'm trying to say is, like, these three basis vectors will span a space, right? So the span of this space, I can find the pre-image of that space. The pre-image of that space is going to be all of P2, right? That's all I'm trying to say. I just counted, Lucas. I don't know how to say it. I just used the ball as an example. So this ball has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's going to be 10 of these on one side of the ball. And then what you have is you have this cap is on the other side of the ball. And then you have the connecting space around the ball. So if this is 10, then the opposite side should also have 10. So the front face should have 10. The back side of this, ball should have 10. And then all you have to do then is count along this like around here. So you're counting the remaining ones that you haven't counted yet, which happen here, 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 which should be 10. So it should be 10 plus 10 plus 10. Yeah, Anders, yeah, exactly. It's the inverse of a restriction of the original function, yeah. The inverse of a restriction you should be able to find the pre-image of the restriction, right? Is basically what I'm trying to say. Like back here, T inverse wouldn't make any sense to talk about. Like I wouldn't be able to define T inverse from P3 to P2. That wouldn't make any sense, right? I wouldn't be able to do that. And I think that's what you guys are trying to tell me, and I completely agree. I would not be able to do that. But I really like the terminology of restriction. That makes it make more sense. So Fem says each hexagon has 3 such edges, so 3 times 20 equals 60, but you counted each one twice. Ooh, I like that idea a lot. Yes, that's a cool idea. I really like that too.
Exceptional, but don't get too comfortable. Now, solve for x, 3i2, 12y. 0. What values of x satisfy this equation? Show your skills or be zeta forgotten.
Yeah, so if we look at each one of these, how many of these do we have? 1, 2, 3, 4, 5. So we have 5 plus 5 plus 1, 2, 3, 4, 5, 6, 7, 8. Is it 10? There's 20 of these such sides. Oh yeah, it tells us that in the question. Right, so 3 sides. Let's do it in blue so it's easy to see. So 3 of these sides on 20 such items. I like that solution a lot, Fem. That's really nice. And makes it a little bit clearer. It's better than just counting. And it's a better strategy than just straight up counting, too. Cool. Well, if we do some more, we have a couple other questions from here we can do for Lucas. But Lucas, if you got to go to bed, go to bed. So that's that. Okay, Onder says that they are curious about number 11. I'm kind of curious about 11, too. Prove that there exists a linear transformation. So we're going from 2 space into 3 space. So what I kind of want to think about is I kind of want to think about 1, 1. I kind of want to do something like this. I want to say that like 1, 1 is this standard unit basis vector and then plus this standard basis vector. We want t to be linear, so we want it to naturally work like this. And we know that this is getting mapped to 1, 0, 2. Which is going to be this basis vector, plus 2 of this basis vector. I don't know if this is helpful, I'm just throwing some stuff down. But I think if I can kind of figure out how t works on basis vectors, I might be able to figure out how t works on 8, 11, right? And I think we should theoretically be able to do this. So for 2, 3, we're going to get 2 copies of this basis vector and 3 copies of this basis vector. We want t to be linear, so it should be 2 of these and 3 of these. And we know that this gets sent to 1, minus 1, and 4, which is going to be this minus this plus this. I don't think I care about this as much. I think what I care about are these 2 things here, right? Are these going to define an equation that I can solve for? Right? Could I just call this like x plus y is equal to 1, 0, 2, and then I know that 2x plus 3y must get me 1, minus 1, and 4. So, I mean, couldn't we just do a substitution now? So 2 times... And again, I'm just kind of assuming that everything's normal. We're working with R spaces here, right? Like R to the n, so everything should be kind of like normal addition and subtraction and things like that. I don't think anything funky is going to happen. And so I should be able to solve for y, I think. Right, so we have that 2, 0, 4 minus 2y's plus 3y's would be equal to 1 minus 1 and 4. So that's going to allow us to isolate y here. That's going to be 1, negative 1, 4 minus 2, 0, 4. So vector y, which is the output of t at the second basis vector, is going to be negative 1, negative 1, 0. Okay, so this is going to be t of 0, 1. That's how we defined y. If we sub that back into x plus y, that would give us x plus this is equal to this. Again, I haven't really justified why this is linear. I'm just kind of doing a lot of rough work right now, right? And most of this rough work is going to help me to figure out what's going on with the second part of the question. So if I get 1, 0, 2, take away negative 1, and 0, what are we going to get here? Brain work. Okay, so 2, 0 plus 1, and then 2 take away 1. So that's that. All right, so with those two pieces of information, we should be able to answer the second question, which what happens to 8, 11? So part 2 of this question is what happens to t of 8, 11? That's just going to be t, well, that should be 8 t's at the first plus 11 t's at the second. So 8 copies of this and 11 copies of this. So what do we get here? 16, 8, 16, and then negative 11, 0. So 16 take 11 is 5, 8 take 11 would be negative 3, and then we have 16. So that should be that. Now as for the first part, how do we know that it's linear? So how do we know... Right, so how do we know that this is like a linear thing? So, in other words, how do I know that I can go through this procedure and figure out what happens to 8, 11? How do I know that there exists a linear transformation? Now, my initial...
Here we go. Let's see the solution of your advanced algorithms come true. Fine, I'll integrate.
Good luck, everyone. Hi, Simplex. Welcome
Time
in.
for a pop quiz.
I see we are both using old-fashioned vector notation.
Problem solved.
I wanted to differentiate it between a regular number, I guess, right? Like, I didn't want x and y to be just variables. I knew that they were vectors in R3. Oh, Joe snags it. There you go, buddy.
Nicely integrated.
30 QED points, damn. Now, I think this has something to do with the basis, right? So how does this work? We know that a linear transformation will exist between spaces that takes basis vectors to basis vectors. I think that's a theory. Right, so if I start with basis vectors in R2, and I map them over into R3, I know that there's a linear transformation that does that. So in the case of 1, 1 and 2, 3, we know that those are linearly independent vectors in R2, so theoretically they form a basis. Right, for R2, well, all we really need is that they span R2, right? So these two vectors span R2, which means I can break them down into basis components, right? So I have the ability to break this down into basis components, and I know that I can construct a linear transformation after I have that information. So that's interesting, because I know the next question is, why does a linear transformation not exist? I think the follow-up question is, why does this linear transformation not exist? Right? Is there a linear transformation from R3 to R2 going backwards, right? Like, pretty much going backwards, right? That I want to map an R3 vector to this, and I want to map another R3 vector to this. All right, so can I do that? It's probably from that one stream where you got back to that. There was a couple streams where, like, I think I, like, walked away from my computer and, like, the QED chances were coming up like crazy because people just kept spinning the wheel. We could take a look at the book a little bit here too, right?
Perfect calculations.
Holy shit.
Deliver perfect results.
Han, oh my gosh. Thank you very much for the tier 1 subscription. Much appreciated. Can you calculate infinity for me? Can infinity be calculated? Yeah, so here we go. So V, so TB linear. Yeah, if I have a basis for the first space, then I know that that basis is going to be a basis for the span of wherever those basis vectors get sent to, right? That's the range, right? A basis for the range. So that's true. Do they give any indication here? Okay, let's rank nullity. Now, I guess we could maybe make an argument through the dimension theorem. Could we? Could we? I don't know if we can, actually, in our example. Right, our dimension is 2. Right, I have inputs that span the space. So the most I can get on the other side would be dimension 2. So maybe you can appeal a little bit to dimension theorem? Oh, here it is. It's this one, right?
Awesome. Linear transformations are like rotating coordinates, essential in both math and physics. Glad you're flexing those genius muscles again. Keep accelerating.
I think this might be the theorem I'm thinking about, right? So if I have 2 vector spaces and I have a basis for V, then there exists exactly one linear transformation that maps basis vectors to vectors in W, right? There's exactly one linear transformation that does that. So this is the existence here, right? So 1, 1, and 2, 3 form a basis for R2. Therefore, T of these basis vectors, there's a transformation that sends these 2 basis vectors into R3. So that's really all we need here, is we just need to use theorem 2.6. And then I assume the proof tells us how to construct the, right, tells us how to construct the linear transformation. Yeah, and this is just saying, if 2 transformations agree on basis vectors, they're the same transformation, but that's not exciting. So I really think we're just appealing to theorem 2.6, right? That if I have a basis in the first space, I know that I have a unique linear transformation. I don't know why. I don't know. That's why I asked you, because you can't calculate infinity? What? I did some linear transformations the other day to help my friend rotate the atoms in a molecule for some modeling. That's really cool. That's actually really cool. Doing for chem honors, that's fun. It kind of sounds like what I was doing. I was doing like character theory, and I was like modeling molecular rotations and vibrations and things like that. It was a really cool project. I was doing it for like water molecules. That was my honors project in my bachelor. And then I went into complex analysis. Yes, Anders, yeah. That would be my take as well. Now, I went a little bit of a step further and I used the standard basis, but I think the argument stays the same, right? That 1, 1, and 2, 3, they span R2, and the dimension is 2. So I theoretically should be able... I mean, I can use either that basis or I can use the standard basis to get this job done. I wonder if is it easier to do? Oh, so I guess there's another way to solve this too. That's maybe easier than what we did. Actually, and I want to write it down because I think this is the answer that I think I want to give. So here's our final answer. But I want to do this one more time because I think there's an easier way to do this now. Okay, check this out. Check this out, chat. Okay, so since 1, 1, and 2, 3. Well, maybe I'll just write it as a set. So since B equals 1, 1, and 2, 3 is a basis for R2, theorem, what did we say it was? 2.6. Is going to guarantee the existence for us. So it guarantees the existence of a linear transformation T that goes from R2 to R3, satisfying the property that we want, right? That T1, 1 is equal to 1, 0, 2, and T of 2, 3 gets sent to 1, minus 1, 4. So that's the existence part. Now, since 1, 1, and 2, 3 are a basis, I bet we could write 8, 11 as a multiple of 1, 1 and 2, 3. And I bet if we all put our heads together, we could probably figure it out relatively quickly. So is that linear combination easy to find? Like 3 and 2? 3 and 2? So I need 2 of these and 3 of these. I like this a lot more. Yeah, you're right, Anders. Our question doesn't particularly care about the uniqueness, but you're right. It's not, that theorem is not just existence, but it does also go through the uniqueness step as well. So here we go. We have 8, 11 as a linear combination of our basis vectors. So that means that T applied to 8, 11 should be, because T is a linear transformation, it should be 2 copies of T, 1, 1, plus 3 copies of T, 2, 3. So, because T is linear. So I can just apply T to my basis vectors. So we get 2 copies of 1, 0, 2, and 3 copies of 1, minus 1, 4. Do we end up with the same answer as before? So 2 and 3 is 5. 0 minus 3, and then 4 plus 4 is 8. What did we get before? Oh. No. 12 and 4. 16. Yes. Okay, sweet. It lines up with all of that really hard work that we did before, too. Nice.
Easy as pie.
Yeah, thanks for the little nudge there, Anders. It was nice to revisit the textbook there to get a more definitive answer, I think, on why the existence works. Now, if we compare that, and that's why I picked these ones explicitly, right? So that we could kind of compare this back to back. So I'm assuming with 12, we're going to say no, right? Because we have that 1, 0, 3, and -2, 0, -2. I mean, that's like that spanning space is only dimension 1. So it doesn't even form a basis for R3. I'm not even going to call it B, I'm going to call it S, because it's not even a basis. So in fact,
Come on, Jeffrey,
oh,
you can do
hi
it.
Jeff.
Pave the way, put your back into it. Tell us why,
Oops.
show us how. Look at where you came from, look at you now.
In fact, if we want to look at the specific dimension here, the dimension is going to be 1. And the real issue we're going to run into is that something's going to break here, isn't it? Right? So, for example, like t of -2, 0, -6 is just -2. So if t existed, right? So if t was linear, then we could factor out that -2 and get 1, 0, 3, which would be -2. That's going to get sent to 1, 1, right? Based on the information that we have, that comes out as -2, -2. But the left-hand side gets sent to 2, 1, right? So we're going to run into a bit of a problem here. So t can't be linear, right? Because we've lost that scalar multiplication property. Dang. Yeah, I think I agree with you, Drew. Like the problem about what's going on here is that we have basically linear. What is it? You have scalar multiple vectors that are getting sent to different spots, right? So there's no way that t can be linear. So you're right. I can probably even just get rid of this appeal to S being a basis. I agree. And we just do a contradiction proof. So by way of contradiction, let's assume that t did exist. Right, and then we've kind of showed all of this. But this is not equal to 2, 1. There. Yeah, so that's nice. We can clean that proof up a little bit with some help here from you guys.
Hardly even a practice test.
Sweet. We are just motoring. Look at us go. There's PR. Just pollen. Wait, PR. I think we did these in the presentation, actually. I think Cluster actually did these for us. Can we talk through these ones? I don't think we need to do too much here, right? So, if I take... I think PR is just polynomials, right? Polynomials of any degree? Is it an infinite degree polynomial? What would that be? On page 10. On page 10. It's like they know that we're going to forget this notation. So it's just nth degree polynomials is all we want. So just nth degree polynomials. So when we integrate, they say that prove that t is linear, which follows from the fact that we're using integration, right? Integration is linear, so I'm not super fussed about it being linear, and it's 1-to-1, but it's not onto. So what happens when we integrate? When we integrate, we're going to add a new term, right? We're adding a constant of integration. Something's weird here. There's something I don't like about this. Okay, they're not forced to be the same degree. They could be different degrees. I think that's what I'm seeing here. So they're polynomials in the sense that they're finite. When happens if infinitely any scalar? Is it finite? Okay, so, I mean, it must stop somewhere, maybe is what they're trying to say. A polynomial, so we could potentially have different degrees of our polynomials, but the polynomial should stop. It doesn't go infinitely in the one direction. So yeah, if I integrate, I'm going to introduce a new constant. I'm also going to increase the polynomial degree, but that doesn't matter. So basically, it's just a shift of basis vectors, right? You're taking the basis vectors of PR, which are all of the x to the m's, and you're just increasing them by 1. So you're shifting it over. Yeah, I see. So it's 1-to-1 because you're shifting the basis vectors over in a very clean way, but you've also introduced this new constant parameter, right? When you do that shift. So it's almost like you're adding this extra degree, right? Like of freedom over here. So could we find a polynomial that would not... So they're saying if it's not onto, we should be able to find a polynomial that doesn't come from some other polynomial, is what they're saying. Is our constant always going to be 0? Okay, I want to think about this a little bit more now. Wasn't as obvious as I thought it was going to be. The linearity is super obvious to me. Like, what breaks down here? Yeah, it might not necessarily be a probability density function, but yeah, we're looking at the accumulation across 0 to x. Maybe I can't even... Is this going to be an infinite dimensional space? I think that's what I'm kind of curious... Like, I'm a little unsure about the notation, that's all. But anyway, what happens when we start, like, looking at basis vector? So, like, what would happen to, like, this first basis vector? Whoops. Okay, so that's kind of rough work. So for one-to-oneness, we really just need that t of some polynomial equal to t of some other polynomial would imply that f and g are the same. So in this case, we're getting like 0 to x f of t dt should be equal to 0x g of t. We could probably subtract these, right, since they have the same indices. So we would get f t minus gt. That would have to have 0 area. Meaning, I guess, one of two things. Either x is 0, or that f of t and g of t are the same. Does that imply that f and g have to be the same? Yeah, because we're looking at the difference of them here under the integral first, right? So well, now I'm not convinced that that has to be true.
What a zero matrix!
Hey, Rescup. how's it going? Why are you trying to redeem all these QED points that you don't got, fam? Yeah, now I'm wondering, like, is this true? I mean, I guess we're working with polynomials. Right, so we are working with polynomials. It's not going to be other weird functions or anything like that. Like, f and g have to be polynomials. But could I make a polynomial so that when I scan the subtraction of them from 0 to x, I get a 0? I mean, probably. I mean, I feel like I could create a cubic polynomial from the difference of two polynomials. So I'm not sure that my proof is going to check out here. Right, like, couldn't I create something... Oh, it's going from 0. Oh, right. And do all of our polynomials have to... They don't have to go through 0, but we can't move them over easily, can we? I was just thinking, like, maybe we could do something like this, right? Could we make... Oh, no, that's not going to work. That's not going to work, right? And since they're polynomials, they will eventually have to stop. They're not going to end up being periodic or anything weird. So yeah, I think we're okay here. I just don't know how to formalize that super nicely. I think because they're polynomials, right, the end behavior is always going to tend towards positive or minus infinity. Right, so as long as I continue to slide x around, I should be okay. Oh, Anders does? Okay, so Anders has a way to think about injectivity. Sure, let's take a look. Oh, of course. Yeah. Yeah. Why are we thinking in terms of polynomials when we could be thinking in terms of the kernel? So, going by definition doesn't seem like the right thing to do. Okay, what is the kernel of this map?
Beep, beep. I'm a sheep. I said beep, beep. I'm a sheep.
Hi, Don. Welcome in. Kernel, I could use some chicken. Totally. Okay, let's go down that rabbit hole for a second here. So I would like this.
Here we go. Let's see the solution of your advanced algorithms come true. Surpass the limit. Time for a pop quiz.
So if we... Oh no, someone got an ad break. No! Damn it.
Problem solved.
Ooh, so close, Don. So close. This is probably the... I mean, like, for any x value, right, this has to imply that f of x is 0. Right, so I think we want this equation, like I think we want this formula to be valid not just for x is equal to 0, we want it to be valid for any 0 or positive value of x. So the only way that this is going to be true all the time is if f of x is 0, right? T is 1 to 1 in this case because the kernel would be that. How do you feel about that, Anders? Does that make more sense? I think that makes more sense to me. That's a lot of QED points, friends.
QED.
So that makes sense to me, but not onto. So to show that it's not onto,
Here we go. Let's see the solution of your advanced algorithms come true. The perfect proportion.
ooh, no ad break, thank goodness.
Time for a pop quiz.
Ooh, that looks hard.
Easy as pie.
What'd you do, Jeff? Did you do like a 20 times 20 and then fiddle around a little bit? Like I'd maybe go like 20 times 23 is maybe what I'd do. Yeah, okay. 20 times 23 would be like 460, but we gotta subtract a couple of them. Yeah, minus 2 23s. Yeah. It's been a long day. I feel like that mentally hurts me right now. Just like working with infinite vector spaces. Okay, so since these aren't finite dimensional vector spaces, the onto thing, I think do we have to do the onto by definition? Can we just find a counterexample? So it would not be onto if I could construct a integral on the right-hand side that doesn't come from a function on the left-hand side, right? So t would not be onto. If we could find one of these. Right, that should come out to be some kind of polynomial, such that t of f of, maybe I'll call this g just for the sake of argument. So we'd want t of f of x that seems hard too. This seems maybe more reasonable than the one-to-oneness, but this also seems pretty hard. Could I show that I can't find an f that makes that work? So Jeff is suggesting that x squared plus 1 can never be hit. We're missing non-zero constant polynomials. Okay, so let's take that as an example. So you're saying the counterexample, and I'll see if I can weave my way through this. So the counterexample is just not obvious to me right away. So the counterexample is g of x is equal to x squared plus 1. Okay, we'll try that. So we need a t of f of x, which would be equal to this. And we want that to be equal to x squared plus 1. Oh, I understand. Yeah, I got you now. I think I see it, right? Because when we integrate, we're going to lose the ability to justify our constant, right? right? So the idea here is that f of t is some kind of polynomial, like x to the n. Those should be t's, not x's. And so when we integrate this, we should get something like this. There you go. Yeah, that makes sense, right? So we can never find coefficients a(n) through a0 to recapture x squared plus 1, right? We just can't do that because there is no constant here. Interesting. Okay. Yes, oh, that makes sense too, right? So evaluating these things at 0. Whoops, why do I have t's here? These should be x's. Cool. Okay, I'm happy we thought about that more. I needed to be reminded of how to do some of this stuff. I knew the integration one was going to be a little tricky. So I'm glad we did that one. So projections, what can we do that's not ridiculously time consuming? Because I got to jump off here to take the dog for a walk and get prepared for our linear algebra presentation. So we have our lin-alg presentation coming up. That's going to be in about an hour and 40 minutes. So it starts at 7 p.m. Pacific time. We have a guest lecturer coming in.
Let's see the solution of your advanced algorithms come true.
And Cluster's going to talk a little bit about... what do we get? Oh, another QED. So Cluster's going to talk a little bit about
Time for a pop quiz.
systems of linear equations in a little bit more detail with us tonight.
Hardly even a practice test.
Nice. Quick fingers. Holy moly. Okay, let's see if we can rifle off one more of these questions before I jump off. Is anyone streaming? Is anyone streaming maths tonight? Other than me? Let V be a vector space of complex numbers over the field R. Define T v to v by T of Z as its conjugate. Prove that T is linear and compute the matrix with respect to beta. Okay, where our basis is 1 and I. Okay, how does this work? So let's take a look at what happens with its basis vector. So T is going to send 1 to its conjugate, which is 1. And T is going to send I to its conjugate, which is negative I. Now, if I'm looking at T with respect to beta, that's just going to be the columns that we get here, right? So I need to convert this into a coordinate with respect to the basis beta that we're working with. So 1 is just 1 copy of 1 and 0 copies of I. And this one is going to be, what, 0 copies of 1 and minus 1 copies of I? So isn't this the one what we're looking for? So T with respect to basis beta should be these as columns. And we could probably verify that that's true because we know that t of a plus bi should be equal to a minus bi, right? It should go to its complex conjugate. And over here, if we're working with vectors, I know that this multiplication of this times, I don't know, some ab with respect to 1 and I should come out to be this multiplication. So 1, 0, 0 minus 1 times AB. So I recapture A, but B gets negated, right? So that should come out to be looking like the complex conjugate of what we inputted. Yeah, that seems okay to me. Did onto hold or not? No, it didn't. It didn't hold. So I took a bit of a longer route by just kind of integrating the polynomial, and then we noticed that once we did the integration, we didn't pick up a constant of integration because we have this lower bound of 0. So I sub in the upper bound of x, and I get x to the n plus 1, blah, 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 down to x, right? Because this a naught picks up a t. And then when I sub 0 in, all of those go to 0, so I get no constant term. So any polynomial that has a constant, we wouldn't be able to capture, right? There's no way that I can find a polynomial that gets mapped to x squared plus 1 because we lose the constant term. Hopefully that makes sense, Doom. What's Poingal saying here? Maybe there's something interesting that you're saying. So, yeah, you're welcome. It's also nice to look at the matrix of the multiplication by a complex number, as in a plus bi. The matrix of the multiplication by a complex number. Z goes to, I see, a fixed complex number times Z. You're looking at that as a linear transformation, right? So I mean, we can go down a rabbit hole here for a couple minutes and see if I can understand what you're trying to say. So you're saying look at so we're going to say fix a complex number. So let's fix a complex number, and you're saying look at the transformation. I don't know if it's linear yet or not, where we do the multiplication z naught times z. Is that what you're saying, Poingalis? Okay, cool. So if that's the case, let's let z be, I don't know, x plus iy. I'm assuming you're going to want me to do this over the real so that we're working with a vector space, I think, here, right? Okay, so what happens here? So this would take us to a plus bi times x plus yi. That's going to give us a x's plus a yi plus bxi. I guess I'm going to go bix. No, let's go bxi. And then let's go, this is going to be by I squared. So it's really going to be a negative by, isn't it? So we can think about this as ax minus by plus ay plus bxi. If you want to think about it in terms of our basis, right? So I'm kind of thinking about this in terms of this basis. So multiplication by a fixed complex number. If I put 1 in here, I should get a So if I put 1 in here, y is 0, so I should get 1, 1. And if I put y is equal to 1 and x is equal to 0, so if y is 1... Oh wait, did I do this wrong? I think I did this wrong. Okay, let's try this again. Okay, so t of 1. That would give me a times 1 minus 0 plus y is 0, so it's going to give me plus b. Okay, so t of 1 is really a plus bi. That would make complete sense because z is 1. Yes, that would make a lot of sense. Okay, cool. And then t of I, that means x is 0 and y is 1. X is 0 and y is 1. We get something like this. And that's going to be negative b plus ai. So t with respect to basis beta would be ab and then negative ba. That looks like a symmetric matrix. So that's no, it's skew symmetric. No, it's not. There's something weird going on here, though. Oh, it gives you a glimpse into the representation theory. Oh. Okay. So if I take this matrix, for example, and I multiply it, I don't know, by some complex number. Where does it go? It goes to ax minus by and bx plus ay. And that should be exactly what we have up here, right? So basically, I think what you're saying is that this matrix has a similar effect when we multiply it by this vector, right? So we're multiplying by this vector, but what we've done is we've taken multiplication by a complex number and represented it as left-sided multiplication by a matrix. That's kind of cool. Okay, so we've represented multiplication by z0 by left-sided multiplication by this matrix. That's a really cool, I think that's a really cool concept. I like that a lot. What's the determinant of this? The determinant of this is going to be a squared plus b squared. A and b are real numbers. So this is always going to be positive. So it's always invertible too. Provided a and b are not 0, this should be invertible. So that's kind of cool. You can kind of tease out a lot of stuff here, right? Like as long as a and b aren't 0, this should be invertible because we would just multiply by the inverse of z0. So yeah, cool. So now you can represent all of these different multiplications by a matrix. Oh, that's how... Okay, that's how... I was wondering how that got put in here. So it's kind of like a rotation matrix too, because we know that multiplication by a complex number not only rotates, but it'll scale and rotate, right? Depending on the magnitude of the complex number we're working with. Cool. So that's also a rotation matrix in disguise. Damn! Don't you love math? Math is crazy.
Hardly even a practice test.
Very cool. Thank you for the reminder about that representation theory. That's fun. All right, I hate to say it, folks, but I'm going to run. That's the end of the bonus stream for today. I got to go get Reese out for a walk, and then we're going to be back in about an hour and a half with Cluster. Cluster's talking about systems of linear equations and some of the theory that goes along with systems of linear equations. So be on the lookout for me to pop back for a third time today for our Friedberg Linear Algebra reading group. And of course, if you're kicking around and you haven't been over to Discord yet, maybe you're new, pop over into Discord. That's our Discord server, and I can help navigate you towards where you need to be if you'd like to get some resources for that linear algebra reading group. You are very welcome, Doom. Thank you for coming and hanging out today. It's been a lot of fun. I've had a great day. I feel like I'm actually a teacher again, you know, Zach? Like, I feel like I'm actually a professor again, you know? Today, I was not a department chair. Today, I felt like a professor. And we were actually having, like, a good, legitimate conversation with students today, with other individuals, right? It was a good day. So it doesn't look like there are no math streamers on, so we're going to raid over into Dexy. Dexy's doing marbles on stream right now, so if you want to just like chill out with Dexy for a bit and play marbles, feel free to do that. And then I will be back in about an hour and a half for that last math presentation of today. And then I'm going to take tomorrow mostly off, but we'll be hanging out with Talos tomorrow, so I'll pop an announcement out to remind you that Talos will be continuing on with his exploratory calculus class as well. So yeah, let's head over. Let's go say hi to Dexy. If you want, you can grab the raid message. And he's playing marbles, so marbles is super chill. Like, you just get to like add your marble to the race and just like watch it as it like goes through the race, and you try not to die basically. Like, you try not to die. So see you all in about an hour and a half. Bye!